Thanks, Cord. So our last presenter is Dr. Leon Van Passan. Leon is an associate professor at Arizona State University and thrust leader within the Center for Biomediated and Bio-inspired Geotechnics. He got his master's and Ph.D. from Delft University of Technology in Netherlands. He has more than 20 years of experience in academia and industry developing bio-based ground improvement methods from lab to the field. He has co-authored over 100 peer-reviewed journal articles, reports, or abstracts, primarily in the field of emerging biotechnics. Recently, he has given up his tenure-track position at ASU for a full-time research affiliation and moved back to the Netherlands, where he joined Boskalis, a large Dutch dredging and marine engineering contractor. Leon.
Thank you. You got the pointer, right? No. All right. So again, thank you for having me here. It was quite a travel to get here, but I'll extend it a bit to enjoy the scenery of Maine. So far, it looks very nice. Very different compared to Arizona, but closer to the Netherlands actually. So it looks really nice. Okay, so yeah, I'm talking about biogeotechnics or bio-based geotechnics. I've done that for the last 20 years. The last 5 years, I spent my career in Arizona at Arizona State University because they got this center from Nsf funded. Question would be, well, why bio-based geotechnics? Well, we have seen other talks today using nature-based solutions. We have a challenge to deal with. To build our society and infrastructure, we need a lot of resource energy, and we have a lot of emissions we need to deal with. According to some legislations, we have to reduce all our emissions to zero. Question is, are we going to make that within sufficient short time? Well, it's going to be a challenge, but if you then look at natural systems, and I always like to look at these pictures. Our task is to reduce 5.5 gigaton, maybe more by now, of carbon emissions in construction industry, among other things. It's a huge task. If you look at the natural cycle of carbon, the fluxes of carbon in the natural system are much larger. So there's about 120 gigaton of carbon going in nature and out of nature. To change the percentage of the natural fluxes may be more easy than 100% reduction of the carbon. And so just to look at the natural system, we may learn ways of other solutions than just fixing this, although this is still, well, it's still a task and a challenge to reduce those things. So so that's part of the mission of why what they made a pitch when they applied for an engineering research center, and that is quite establishment. It's a big pot of money provided by Nsf to do research on these bio-based solutions. And in 2015, Ed Kavazanjan, director of the center, teamed up several highly reputed academics, and he wrote this proposal. Very small chance of success, but he managed to get so, and I think it's the only research center in the civil engineering realm. So once he got it, he gave me a call. We had the same type of research interest. He said, "Do you know someone?" And I said, "Well, it's something different for a change." So I moved to Arizona, joined Arizona State University, and collaborated for over the last 5 years with academics, mainly from Georgia Tech, New Mexico State, and UC Davis. It's research, but it's different research than the standard research you would apply for when you apply for proposals on Nsf, because Nsf typically goes for fundamental research mainly. You have to write a broader impact statement when you write a proposal, but it's all about bringing the state of knowledge to a higher level, whereas the Engineering Research Center has a different objective. It's not only fundamental research, you also have to spend money and time on bringing these innovative solutions into the field. So how do we do that? Obviously, by selecting the type of projects which have a higher probability of implementation. And second, by having an industry partner program, among which CORD is one of the active members. And they are judging our proposals, see if there's potential in it. And then, well, that helps us with deciding which projects to fund and which not to continue. So The mission of the center is to learn from nature and use these natural processes to transform engineering to a more sustainable system. We have separated biomediated geotechnics from bio-inspired geotechnics. And biomediated uses the nature directly, and bio-inspired uses nature as an inspiration. And as an example to explain that, one of the projects I'm involved with is bio-based scour protection. And you can use mangroves, a natural system, to mitigate scour along coastlines. But if you want to mitigate scour along bridge piers or monopiles in offshore wind farm applications, well, you cannot grow mangrove at that large a depth, or the environment may not be suitable to really build that natural system, but you can then learn from the natural system to come up with a solution like micropiles surrounding your foundation structure and blocking that wave energy. And so that is one of the biomediated versus bio-inspired type of applications. So main part of the talk is, main part of the research I have been involved with is biomediated ground improvement. Cord talked about several ground improvement methods, and Aaron has worked with other methods to try to improve the properties of the ground. If you want to do that bio-based or biomediated, you have to look into what kind of biological processes take place in the subsurface. Can we use those processes to change the properties of the ground in the direction where we want them to be changed in? So we have to know about biological processes. We have to know about mechanics. Well, biological process in general is a catalyzed chemical reaction. So we have to understand the chemistry of subsurface processes and then try to steer the chemistry in the direction where we want it to be. And then the last part, the right down corner, is field application. In the end, within the center, we have to bring that to a full scale application and trying to see what's the commercial value of these particular processes. If we look at the different products, it can be minerals, can be biological matter, or it can be biogas. So the main process I have been looking at, and I've been looking at already when I did my PhD back in the Netherlands, was biomediated ground improvement using induced carbon precipitation. So we take a resource, urea, it's a fertilizer coming from urine. So we have projects trying to extract the urea from urine, and we had on campus, it was P for science, or we had a collection station, and then we had biological scientists trying to extract the urea and then use it as a resource in this process. If you mix it with a calcium chloride solution and you come up with some bacteria which have an enzyme urease, they catalyze the hydrolysis of the urea to ammonium and to carbonates. And when you mix the carbonate with the calcium, like Aaron showed, you get minerals, and these minerals can cement the soil. So it's a chemical reaction with a biological catalyst. So I studied the process, and we already had at that time during my PhD was, can we scale this up? Because it's a chemical reaction, it's known in literature, but how do you make an application out of it? Well, you have to demonstrate that it works at the scale of the application. So that was my task in my PhD program. I knew that this was possible by my predecessors, and then I scaled it up. Well, first thing is, one of the competitive advantages we anticipated was we can inject it over a very long distance compared to traditional mixed chemical stabilization methods, which can be injected, but you need a lot of pressure and you have a limited injection distance. Here we wanted to try to see if we can inject underneath an existing structure. So we need to have large distance. So we demonstrated 5 meters in 2005, but then, well, it got stuck because what else do you do at a university? And you cannot, well, build these large infrastructure systems. So you have to talk to industry, and luckily this project had industry partners. So they helped me to provide materials, and well, this is the thing I did myself in the backyard of my university, 1 cubic meter box, injecting the nutrients and the bacteria and then showing that it works. And then they said, well, once I've seen how you did that, so let's bring this to a larger scale. We went to the yard of the contractor and they built a sandbox and they installed the wells they typically use in traditional technology systems, pump and treat systems. And they injected the same recipe and we managed to scale it up again to 100 cubic meters. So demonstrated, end of PhD, very successful, but not yet commercial, right? So the next thing is, well, what are the applications? It's interesting that you showed demonstrate the feasibility. So there were many different applications. I was not the only one working on this process. Many different others, well, they also read the literature and they came up with a lot of potential solutions where you could use this process. So yeah, but what's next? I just graduated. Where to go? Well, luckily the contractor had a friend at another contractor, and he told them about it, and he said, I actually have an opportunity. So he was constructing this major gas pipeline network. He would not do that anymore because gas is banned. But it could be cables, and one of these well, at some stage the Netherlands thought, let's become the hub for gas distribution in Europe. So they invested a lot of money on these large gas pipelines going through the country, and one was crossing a river. And crossing the river was okay, but it had to cross several gravel layers, and they used to construct them with horizontal directional drilling, which is very risky in gravel. So they said, well, we can take the risk, but then we want extra money. And then we apply this new technology. They knew that the risk was acceptable for the contractor. They just got the extra money, gave me 200,000 euro, and then they kept 100,000 euro themselves, I think. But then at least I could, oh, well, not me, with them, we could try and see if it would work on a larger scale. So we have implemented it. We've demonstrated a large box, drilled through it, showed the client, look, we can stabilize gravel, and the hole is stable. So then you see what it takes to do this at the larger scale. Injection wells, extraction wells, pumps, manifolds, large resources. So, okay, so a few conclusions here. We demonstrated it worked to a certain extent. We did some geophysics showing before, during, so there's a change, so that's good. What does it mean? Is it enough? How do you sample? It's below groundwater level. You have to take samples. It's a little bit cemented, but how do you get a slightly cemented sample up at surface? It's quite a challenge, as it will break apart. You cannot really do a lot. So he brought a handful of evidence that yes, it was cemented, and it smelled like ammonia. So that also meant that the process had worked. But overall, contractor was happy, client was happy because the pipeline went through without any problems. So that was the evidence that it worked. We demonstrated, yes, it worked. We had experience with injection mixing method, but as a scientist, I would say, yeah, it's not yet ready for commercialization. And we haven't proven that it's not in the standard yet. I think the court listed a few things and what is required to accept these kind of technologies. So we still have limited evidence that it actually worked. How much did it work? What was the strength we gained? The natural variability in a gravel. How do you characterize a gravel when you do ground investigations? Quite difficult to get strength data in a gravel using cone penetrometer testing or sampling to really prove that because of your method, it worked. It worked, but how to prove it? Secondly, we found that, well, it's a biological process, but biology still requires resources. These bacteria need to eat, they need to resources. It's about $400 per cubic meter of soil, which is okay, similar to cement injection, but well, if you can choose between the existing cement method or something new, which may work, but you don't know how much, well, the comparison is easily made. Nature-based, so we've had people say it's a biological method, so it's good for the environment. Well, not necessarily. You produce a lot of waste, which has environmental impact. Same as, so using cement, you have CO2. Well, using urea, you produce ammonium. In the Netherlands, we have half of the country shut down because of too much ammonium in the subsurface, and we had to cut down our nitrogen deposition levels. So now in the Netherlands, this would not be an acceptable method, and we have to reproduce it again. So at least it gives opportunities so we can shift our efforts. Well, we have this experience. Well, maybe we can learn from this and come up with new ideas. So other applications, other processes, other products. So other processes, after done that, I looked into other biological processes. So there's many. Second best alternative would be nitrate reduction. In this case, we use calcium fatty acids and calcium nitrate to produce this, again, calcium carbonate mineral. And now as a byproduct, we only have nitrogen gas, inert, no problem. Bacteria, also no problem. Actually, we don't need to inject bacteria anymore. We just grow whatever is out there. They're already there. We just need to feed them. We have to feed them the right food to do the right conversion. Eventually, even we could use waste streams. So calcium fatty acids, it's like fatty acids are organic waste streams from sugar industry or paper industry. Mix it with calcium carbonate or lime, and you get calcium fatty acids. Calcium nitrate is waste from our sewage system. mix some calcium carbonate in the system, you get calcium nitrate. So mix these two waste streams, put them in the ground. Okay, some environmental legislation issues maybe, but putting waste in the ground, who wants that in their backyard? I don't know. Other products, and this is where I met Aaron. We can use the gas, the nitrogen, which is the byproduct of the mineralization process. We can also use that potentially. So one of my colleagues, he came up with the idea, if we inject the nitrogen, they did it in Japan a lot, inject gas in the ground. If you have an unsaturated soil, the gas is compressible. And when this happens during an earthquake, saturated soil, when they start to shake, they may contract, and as they contract, water wants to squeeze out, and as a result, it may liquefy, and you get things like this. If you partially saturate it, so you inject some gas or you form some gas in the ground, the gas is compressible, and as a result, they take up the blow and they dampen those pore pressure buildups and prevent the ground from fading. So nice concept. Again, we pitched it, we got some additional funding or approval to use the funding, and we found actually a potential location in our colleagues in Portland. So Portland is on the Cascadian earthquake line, and they expect in the near future, when we never know, but a magnitude 9 earthquake. If that would happen, you can see all the areas in purple in city of Portland will be liquefied. Here's the international airport. International, I don't know, but the airport. And here's the energy hub for the entire state of Oregon. So all the oil reserves, all the electricity stations are all, they're all based or founded on liquefiable soil. So if this would happen, they have a major catastrophe. So they pitched it, and they got a lot of response from their local authorities to put some effort into this. So we teamed up with the colleagues in Portland and did a field trial on trying to see if we could inject the same nutrients and prove that there's actually gas forming there. So we proved that the gas was formed and it was desaturated. However, you can see here in the bottom, there's a big shaker machine from University of Texas trying to shake the ground and mimic an earthquake. We tried. Yeah, there's a movie, but now you can click on the picture and you can see the water box shaking. But you can imagine we tried to shake it really hard, and you could, if you would stand near it, you would see the water going back and forth completely. Here it goes. A small earthquake. Earthquake was not strong enough to generate any pore pressure buildup. So it doesn't mean it works, or it doesn't mean your machine was not heavy enough, right? So that's still an uncertainty. So we demonstrated desaturation, but did we demonstrate real resistance? So we still have limited evidence. We still don't have methods to prove that it's there and whether it persists. So luckily Aaron came along and he proved theoretically that it will stay there for another 100 years. But so it is a question we often get. Still, we can think about the environmental impact. So one bonus point for this method is that if you need the gas, you just need a little tiny amount of gas compared to the minerals. So you need 50 times more substrates or nutrients to put in the ground to generate sufficient carbonate precipitation versus injecting these nutrients to generate some nitrogen gas. So there's a huge difference in cost. But then, comparing nitrogen gas with cemented soils, complete different products. So how to deal with that and how to get that into the standards, into the end users and public authorities to try to use these technologies. So then you go for, well, how to commercialize this. Question is, are we doing that? We get a lot of questions. Luckily, NSF has again an instrument to try to stimulate that. So we joined the Nsf I-Corps, which is you get 7 weeks full-time training to interview with all potential end users or partners or influencers to try to find out if you have a product which is commercially applicable. At that point, me and my student, after 7 weeks, we were devastated, and we said, well, as an academic, I don't have time to also start my own business, right? I also have to teach. I also have to write proposals and all that. So as a student, just graduated, well, maybe first get some experience. But at least you get the information whether it's worth to start a company. If we're not gonna do it, well, we have our partners which listen to what we say and maybe see an opportunity to either do it in a business model or well, we also have clients sitting at a table and thinking, hey, this is maybe a good idea. So what I always found in all these trials, we had major input from our industrial partners. Just applying the equipment, using the equipment, providing feedback on how to pump it in. I can do a column test, but I have no, I don't have like large pumps, install wells in the ground, in the subsurface. So general future about an innovation like Biogeotechnics. Yes, we have proven technically it works. This is just two processes. So we've seen plans for stormwater management. Plans for stabilization is an option. You think 35 million is a lot, but still, yeah, it's limited. You cannot spread it thin and spend one PhD has to spend his 4 years to try to get something to a high level, both in technical understanding. So there's a lot of opportunities, I think, to be explored, considering how to commercialize these things, how to bridge the gap from lab to market. I think you really have to work on your value proposition. So your technology should be equal or better, providing an advantage for the end user. Find the right application for it and the right partners to work on that application and demonstrate that it happens on the field. So we're successful in some of those, but we're not there yet to the full commercialization. Yeah, what it means to me, I shifted now back to the Netherlands for personal reasons. Family wants to move back home. But I also switched from academia to industry. So one way would be as academics trying to see things to implement it, just join up and team and join the contractors. And now we're trying to see if we can use it on, so Boscala is my current employer. They're building large islands from soft soils, from sand. They need to do a lot of compaction. I may be a bit competing with Cord on some of the aspects, but so obviously we try to see where it can be implemented in the industry. So that's the future. Many people, students, but also partners I'd like to thank. And thank you for inviting me.